Okay, so now we will talk about the change in period and separation during the mass transfer of this binary system. As you have already thought about, so basically our main idea is Roche law, right? Now in this case, one is a donor star and another is a receiver star. So in this case, if I am saying that this is a donor star, then this means that this Roche law must have been filled, right? This Roche law must have been filled, and then what will happen if the Roche law is filled? The spilled amount of mass will then get transferred to the receiver star. Donor star, receiver star. Now, here we have to consider two particular scenarios. One is conservative mass transfer. What is conservative mass transfer? Conservative mass transfer means whatever mass is lost by the donor star, the receiver star is able to entirely absorb all of it. So this means the entire mass is conserved inside the two-star system, binary star system. This is conservative mass transfer. Then we have got non-conservative mass transfer. What is that? It is whatever mass is lost, some of this mass lost by the donor star is not being received by the receiver star, or you can say the receiver star is unable to absorb all the matter that is flowing from the donor star. So in that case we will have non-conservative mass transfer. Now we will consider particularly the case for conservative mass transfer. Okay, some basic mathematics before we discuss more about Roche law. So period of a binary in circular orbit, of course it's given by Kepler's third law, this one. P is the period, okay, omega is the angular velocity, and this is the expression. Next, angular momentum of the system around the center of gravity. We will call COG in short. So this is the angular momentum expression, m1 a1 v1 plus m2 a2 v2. These are the masses of the two systems, m1 m2. We have already discussed this. And a1 is the distance of system 1 from the center of gravity, same for a2. And v1 is the orbital velocity of mass m1. Here you can see a1 plus a2 is the total distance a, and center of gravity is defined using this relation m1 m1 is equal to m2 a2 is m1 m2 a by m1 plus m2, and the velocity, full velocity is v is equal to v1 plus v2. You see I have just written omega a1 omega a2, so this is just omega into a. Now if we use all these relations, then we will get the total angular momentum in the compact form. So G A into m1 square m2 square divided by m1 plus m2. Okay, so conservative mass transfer. Basically, we are defining the conservative mass transfer through these two equations. Mass, entire thing is conserved. So this means whatever is lost by one will be gained by the other. Simple. So m1 dot negative or m1 plus m2 dot equal to 0 basically. Again, angular momentum j dot equal to 0, right? Conservative mass transfer. Now you also remember that we have, right, what? We already found the expression for the total angular momentum j just a few minutes back, right? Now let us differentiate this. So you must be wondering, sir, why differentiation? See, what we want is basically how the two stars will evolve with time. Roche law is just an indicator, right? So evolve with time. So this means we have to see the evolution with time. That means we have to do differentiation over here. So let's do the differentiation and you can check by yourself that you get this. So you have checked, right? So you will be getting this result. Next, we include the conservative criteria. So if we put these two conditions in this equation, we get down over here. Any questions? Nothing. No question. Now, before moving further, you have to understand that if M1 is the mass for the donor star, then M1 dot will be negative, since it is giving away mass. So M1 dot is negative and M2 is the acceptor star, so M2 dot will be positive, right? Now let's see. See? So first let us consider this case, that the donor has more mass than the acceptor star. M1 is better than M2. Okay, so A dot by A here equal to what is this? M1 dot, donor. So this is negative. So basically 2 M1 dot by M1 is a negative quantity, negative number, into M1 minus M2 divided by M2. What is this? M1 is already more, so this is a positive quantity. So this means that overall this will be a negative quantity, or A dot is less than, or basically this is negative, right? What does this mean? The radius will shrink. This means that the radius will shrink. So basically if the Roche lobe is like this, see, this is M1, this is M2, right? Bigger mass, okay? And this one is the donor. As a result of this mass transfer, what will happen is the separation, it will decrease. So with time, what will happen? They will come closer. Something like this. See, the overall separation from here to here has decreased. So this is the result. Okay, next, if M1 is less than M2, then this will be, M1 is less than M2, so this will be a negative quantity and this will be a positive quantity. And so, in this case, the radius will expand, right? So if this is the one which is donating M1 in this case, then what will happen with time, since, so overall this will become smaller, but this one will become even more, and overall the distance will be larger than this one. This will be larger. Any questions? So basically this is how we discuss the change in distance and the effect of mass transfer. Okay, an angular mode for conservative mass transfer.